Hello everyone, this is Professor Iris Miano giving you your Day 24 lecture video for Math 50 Pre-Statistics, covering two of my favorite topics, exponential and logarithmic functions. So this spans sections 11.1 and 11.2. You won't find these sections in your textbook, so the lecture notes that I provide here, and also there's a version of this in your workbook as well. That's the extent of the materials that you're going to be given in this class. Just to be clear, there's no textbook sections covering these. So these are department created sections. Okay, let's get to it and go ahead and define exponential functions here. So this is a function of the form f of x equals a to the x power is called an exponential function. Nothing earth-shattering since it's also defined right here in the heading of this box. Some things to remember about exponential functions is that the domain is all real numbers. You could put anything you want in for x. All real numbers is all real numbers. But the range, the output that you can expect here with this parent function, and by that I mean no vertical or horizontal shifting, is all positive numbers. Depending on the value of a, the base of your exponential function, at which a can span anything greater than 0 onward. But if a is between 0 and 1, then you're going to have an exponential decay. So I'll call that a decay model. Whereas if a is greater than 1, you're going to have a growth model. And whether it's decay or growth, you're going to find that the trajectory of the line either goes to 0 if it's a decay very quickly, or it grows infinitely large very quickly if it's a growth model. Okay, so let's go ahead and graph this exponential function, a relatively simple one of f of x equals 2 to the x power. So the first thing I think we should do is make an f of x table. And remember, x can be any value that you want. I choose these standard 5 inputs for pretty much any function, just to get an idea of what the curve looks like. And then if you need to plot more points after that to get an idea of how the trajectory is curved, by all means, you can always graph more than this. So if I plug in a -2 value for x, I'm going to get what for f of x? Well, we can go ahead and calculate this along the way. We could extend this chart to include the calculations. That'll be 2 to the -2 power. Remember your negative exponent rules? That's the same as 1 over 2 to the second power, which is 1/4. Okay, we could do the same here for a value of -1 in the exponent. That'll be 2 to the -1 power, which is the same as 1 over 2 to the 1 power, or 1/2. Anything to the 0 power is always going to be a 1. So that's 2 to the 0 power. Here, let me go ahead and actually draw the calculation here just to be consistent. 2 to the 0 power is a 1. 2 to the first power is just 2. 2 to the second power is 4. So those are our ordered pairs here, basically. It's like here is your x values, and here at the end of the calculation is your corresponding f of x value or y. Y and f of x are the same, so I could just have this be equal to f of x, just as a note to remind myself that those are equivalent. Okay, so let's go ahead and plot these ordered pairs. We have -2, 1/4. So here's -2 on the x-axis, and 1/4 is going to be halfway between halfway on these two tick marks. So maybe about right there-ish, okay? And then my next ordered pair is -1, 1/2. So at -1, I'm going to go halfway up, like so, slowly growing here. At 0, I'm going to have an output of 1, so that's also considered the y-intercept. And then at 1, I'll have an output of 2. So that's the ordered pair 1, 2 here. And the ordered pair 2, 4 looks like so. And so you can see that there's a curve that's forming here. And in fact, it just kind of curves up very sharply after 4. Like for instance, if you wanted to, for the sake of understanding how sharply this curves up, you could have another output of 3, or input, excuse me, of 3. And that would yield what? 2 to the 3rd power equals 8. Oh my goodness, do we even go up to 8? 1, 2, 3, 4, 5, 6, 7, 8. Yes, I can plot that one if I want to. So that's 4, 5, 6, 7, 8. Yes, and so you can see really pretty clearly how fast this curves up. And so what's happening on the other tail end right here? Am I ever going to cross this x-axis? Well, no, you won't, because there's no vertical shifting here. So you will find that if you go more points in the negative direction, you're just going to get a smaller fraction as you go. Like for instance, I won't necessarily put it in this chart, but we can entertain the idea of having a -3 input. That would be 2 to the -3 power, which would be 1 over 2 to the 3rd power, which would be 1/8. And then it'd get smaller and smaller, 1/16, 1/32s, 1/64ths, right? So it's getting infinitely close to the x-axis, but it's never going to cross it. So I'll go ahead and switch the colors just to make it really pop out. We'll go this lighter tealy blue so I can draw the trajectory. And so I'm just going to, the best of my ability, follow the trajectory, but it's going to be a little bit, you know, not exact. It might be a little bit squiggly, so just bear with me, folks. I am going to ride the x-axis and then kind of loop up, going through all of my points, and just try and draw yourself, you know, to the best of your ability, a curve that goes through all the points. You don't want to be super choppy and try and make like straight lines from point to point. That will not be a very good representation of what's going on here. Just try to make a curve that goes through all the points that you plot, and the more points you can plot, the better. The standard 5 usually gives you a good idea, but like I said, it's always fine to plot an extra point. I plotted a 6 point here because I had room within the window of my, what do you call it, coordinate plane. So there you go. There is f of x equals 2 to the x power right there. Gorgeous. All right, let's do some more graphing. And I'll have the same process here. Okay, so I'll start with a f of x table. I'll begin with my standard 5 inputs of -2, -1, 0, 1, and 2. And if I decide to do some more, you know, I can choose to do that later. And that'll give me a 1/2 to the -2 power. Okay, so I'm going to flip over this fraction and call it 2 to the 2nd power, because that's how you deal with a negative exponent on a fraction, just to be clear. So that'll give me an output of 4. These are going to seem very familiar, but kind of backwards compared to the first example that we did. So this next one will be 1/2 to the -1 power, which will give me a 2 to the 1st power, which is just 2. 1/2 to the 0 power is going to be a 1. 1/2 to the 1st power is just 1/2. And 1/2 to the 2nd power is going to be 1/4. Cool. So I'll plot these 5 ordered pairs. We have -2, 4, -1, 2, 0, 1, 1, 1/2, and 2, 1/4. And as you can see, we're exhibiting some decay here. We're about to ride the x-axis, but as we move forward in x. So we started off really big, and we got really small, and that's because the base of my exponential function was a fraction, you know, less than 1 but greater than 0. So a proper fraction, you could say. All right, so I'm going to start from over here and just say that I'm really, hold on, let me erase that first mark. close to the x-axis as I start the process of drawing this trajectory. And I'm going to go through all of the points and then, yep, kind of just have the trajectory climb really far. So as far as this function is concerned, the idea is that you want to think about this as moving forward in x, so movement from the left of the coordinate plane to the right. You are decaying your model. So the output is like essentially going as infinitely close to 0 as it can without actually ever touching the x-axis, so it never technically takes on a value of 0. Okay, cool. Moving on, let's graph one more, and this one's going to have some vertical shifting just to show you guys that how the range will change given some vertical shifting. All right, so here is my first move. Again, I'm going to go x, f of x table, standard 5 inputs. I can choose to do some more if I like. And then my f of x here will be 3 to the negative 2 power plus 2, which equals 1 over 3 to the second power plus 2, which equals 1/9 plus 2, which equals 2 1/9. In fact, I'm going to go ahead and just erase this last bit and just say that I know that the output there is going to be 2 1/9. Okay. Negative 1 is going to give me 3 to the negative 1 power plus 2, which is going to be 1/3 plus 2, aka 2 1/3. 0 is going to give me 3 to the 0 power plus 2. 3 to the 0 power is going to give me a 1 plus the 2 equals a 3 output total. 3 to the first power plus 2 is 3 plus 2, aka 5. 3 to the second power plus 2 is going to be 9 plus 2, which equals 11. Great. So let's go ahead and plot these ordered pairs. 2 1/9 being the output on a negative 2. That's going to put me pretty, like just a smidge over the 2, not quite on the 2. Sorry, let me draw that one more time. So back by 2, up 2, and just a little bit above it, like so. Okay, and then for negative 1, I'm going to be 2 1/3, so a little bit up from there. Not quite halfway up, but 1/3 of the way up. Then at 0, I'm going to be crossing the y-axis, or the f of x-axis, however you like to think of it, at 3. And then at 1, I'm going to be up to 5, so that's right here, 1, 5. And then 2, I'll go up by 11, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Whew, just enough. Okay, and so since this exponential function got shifted up by 2, this horizontal line at 2 kind of becomes the new asymptote, so to speak. Okay, so I'm going to go ahead and just, in this like light green color, just draw a horizontal line, like dashed line there, to indicate that that's the new uncrossable line, whereas the x-axis for a parent function, a non-vertically shifted line, would be where you can't cross. Okay, so now this tealy line is going to represent the function itself, and I grow. Okay, so hopefully that's enough information for us to feel good about being able to draw these exponential functions, particularly when they have this vertical shifting. Okay, great, cool. Now let's go ahead and introduce a new rule, a principle, if you will, that's going to help us solve exponential equations. And it's called the principle of exponential equality. And it goes like this. For any real number b such that b is not negative 1, 0, or 1, and it's the base of an exponential function, then here's the rule. B to the m power, if it's equal to another exponential function of the same base but a different exponent, if this is something that you're given, then you get to conclude that the exponents are equal to each other. It's kind of like you're canceling out the bases. Okay, so here we go. or dropping the bases, as I like to say. Drop the bass. I don't know, makes me think about like EDM music, raver party kind of stuff. Drop the bass. You get to drop the bass and set the exponents equal to each other. Okay, so what do I want to put here as comments? I want to say that so as long as bases are equal, exponents are equal. Okay, but you might have to, and you're going to find this to be true in the exercises, the examples that we're about to go through, might need to force a common base if it's not already there. And I'll show you what I mean by that. Force a common base. So for instance, looking at number 1 in the series of examples here, notice that the base on the left-hand side of the equation is 9 to the x power, right? So we're going to solve for x. And then the base on the right-hand side, I mean, we just have a single number, 27. You could think of it as 27 to the first power if you want to. Okay, that's fine. Or, you know, just say to yourself, all right, I need to figure out what... how this 9 and this 27 can be rewritten as exponential expressions of the same base. So if you're thinking about 9 and 27 and thinking to yourself, oh, well, they can be both rewritten as something base 3. And by that I mean 9 is equal to 3 to the second power, and 27 is equal to 3 to the third power. Okay, so use that fact to rewrite each of these exponential expressions as base 3. So I'm going to put off to the side that the common base here should be base 3. So therefore 9 equals 3 squared, and then it's still being raised to the x power, right? And then 27 can be rewritten as 3 to the third power. So you see how I've just rewritten those bases in terms of a common base, and that what I have written in this tealy color is still equivalent to the original problem. So I haven't changed anything about the problem. I've just given it a little bit of a makeover, such that if I, in the next step, use the power rule to multiply these exponents, then I'll have exponential expressions on both sides of the equation with the same base. Now you can use this principle of exponential equality to drop the bases. Check this out. I'll do this in kind of this red color. Boop, boop. Cancel out the bases and let the exponents be equal to each other. So now 2x equals 3. Divide both sides by 2, and you'll get that x equals 3 halves. And you can call that good. That's done. Okay, let's do this for another number 2. And say to ourselves, okay, the bases currently are 8 and 16. What common base can they have? And I know what you're probably thinking initially with the 16, you're like, oh, I can write that as base 4. 4 squared equals 16. Yes, that's true. But can you rewrite the 8 as an exponential base 4? Turns out you cannot, okay? Because 4 to the second power is not an 8. You know, you don't multiply the exponent and the base to get the value of the exponential expression. You repeat the base as many times as dictated by the exponent. So the best you can do in order to get a common base here is to make it base 2, because 8 is 2 to the third power, 16 is 2 to the fourth power. So here, this one will be, in fact, I want to change the color here. We'll go green with this one, dark green, that is. So here we're going to do this one base 2. And so that means 8 is going to be rewritten as 2 to the third power, and then it's further raised to the x power, and 16 is 2 to the fourth power. Okay, do the same thing we did for the previous problem, and multiply those exponents via power rule, and we'll get 2 to the 3x power equals 2 to the fourth power. Now that you have exponential expressions with the same base, you can drop the base. Boom, boom. Now 3x is equal to 4. See how easy that is? Once you figure out the common base, then it's easy. Divide both sides by 3, and you'll get x equals 3/4, or 4/3 rather, excuse me, 4/3, what I meant to say. 4/3. Bing, bang, boom, and we are done. A couple more exercises, and then we'll be, oh yeah, we'll have a modeling exercise after that. Forgot about that one. Okay, here, this one is a little bit more challenging, but nothing we can't handle. We have a 5 base exponential expression on the left-hand side and 625 happening in a denominator. So you might be thinking negative exponents are in play, in which case I would say yes, good call. That is absolutely true. Let's go this pinky kind of magenta-y color and say to yourself, all right, I'm thinking 625. Can I rewrite that as something base 5? Turns out you can. So this is going to be rewritten as a base 5. And so notice that the left-hand side is already base 5, so I'm not going to change anything there. So you got to ask yourself, what is 5 to what power is going to give me 1 over 625? Well, first of all, I know that since the the number in question is in the denominator space, oops, I meant to erase that. That tells me that the exponent is going to be negative, okay? And then how do I get to 625 with a 5? Well, 5 to what power gives me 625? I want to say it's, let's see, 5 to the, play around with this, times 5 times, just keep multiplying 5s to each other. I got 3 now, at the moment is 125, times another 5 is 625. So it looks like it's 5 to the 4th power gets me the 625, but in order for that 625 to end up in a denominator space, I've got to raise my 5 to the negative 4 power, okay? So there's some playing around that you might have to do when the numbers are quite large, but it's, again, it's nothing we can't handle. Great. So let's go ahead and recognize that we can now slash away those bases, drop the base, and therefore x equals negative 4. That was relatively quick. Equals negative 4. Boop. Donezo on that one. Great. Okay, so for this next one, the common base that could be happening for this next one is, there's actually 2 correct answers. One of them is more complicated than the other one. I would recommend that you go for the largest collective base or common base that is possible, and for this one it's going to be 4, right? Because 16 can be rewritten as 4 to the 2nd power, and then we already have a base 4 on the left-hand side of the equation. You could, though, rewrite them both as base 2, where 4 is 2 to the 2nd power and 16 is 2 to the 4th power. But, you know, like I said, extra level complication that I think is unnecessary. I'm going to choose to do this base 4. In which case I will not even change the left-hand side of the equation, 3x minus 1. And I will rewrite the 16 as 4 to the 2nd power. And then that's going to be collectively raised to the x plus 2 power. All right, which I'm going to put in parentheses because this exponent right here needs to, hold on, get distributed here and there, okay? So then what do? We will rewrite this as 4 to the 3x minus 1 power equals 4 to the 2x plus 4 power, distributing this exponent over this binomial exponent of x plus 2. Okay, now we are ready to drop the bases because we have exponential expressions on both sides of the equation with the same base. Now the exponents can be set equal to each other, and then it's a linear problem from there on out. So that'll be 3x minus 1 equals 2x plus 4, which you can start this next problem any way you choose. I'm going to go ahead and subtract 2x from both sides, and I'll get x minus 1 equals 4. Add 1 to both sides, and you'll get x equals 5 as your final answer. Great. We have one more exercise where it's going to be application centric. So let's change the color to this, I guess, dark purple, sure. Modeling with exponential functions. Here we go. Okay, so here we're given an exponential function outright, this p of t, which p is the percentage of smokers who, without telephone canceling, have successfully quit smoking after t months, and it's approximated by this model. Okay, so the time frame is in months. That's something to keep in mind here. We want to use the model to estimate the percentage of smokers not receiving telephone counseling who are successful in quitting. So basically, you just want to use this function with a t of 1 to answer part A. So this means t equals 1. Plug and chug, basically. And here for part B, the time frame being 1 year, well, how many months are in 1 year? 12, right? So for this one, you're just going to plug in a t equals 12 into your function. Okay, so let's go ahead and do that. So this will look like p of 1 is equal to 9.02 times 0.93. Oops, erase. 0.93 to the first power. And so be careful, because even though essentially you'll just be multiplying these numbers together, it's because the 0.93 is being raised to the first power. What you want to always make sure that you do with these types of functions is to implement the exponent value first and then multiply the number out in front. Okay, so 0.93 to the first power, which is 0.93, times 9.02 yields 8.36 or 3886. 9.3886. I'm just going to go ahead and initially write down the entirety of what my calculator outputs, and then I'll determine an appropriate amount of rounding, which I think will be to the hundredths place, because all of the numbers in the established model were rounded to the nearest hundredth or 2 decimal places. Okay, and again, it's a percentage of smokers, so I think the appropriate final answer will be 8.39, rounding to the nearest hundredth, and put a percent. And so this is the percentage of smokers successfully quitting after 1 month. For 1 month, successfully quitting for 1 month. Just put a little bit of closure on that calculation. Okay, let's do this again, but this time t is going to be 12, so it's going to be p of 12 equals 9.02 times 0.93 to the 12th power. Again, be very careful here and make sure you take 0.93 and raise it to the 12th power, and you're going to get what, 0.418596 blah 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 blah, and then multiply that by 9.02. It is very easy to fall into the error of multiplying these numbers first and then collectively raising it to the 12th power. That's not what this function is doing. What it's doing is it's taking the 0.93 and raising it to the 12th power and then multiplying the 9.02 after that. So syntax and performing these operations in the correct order, using order of operations literally, is so important to this exercise here. Okay, so typing this into my calculator correctly, I get 3.775738.603. So that's the extent of what my calculator gives me, ... It continues forever, but I'm going to round it to the nearest hundredth and say that for this particular scenario, part B, we have 3.78% is the percentage of smokers that successfully quit after 1 year. Okay, so again, be very careful with your process here. Let's do this again, but with another type of model. This one's going to be an exponential growth model. And we need to recognize that the time frame is in minutes. So T is in minutes, okay? And it's this model's modeling the bacteria Escherichia coli, or E. coli, right? Commonly found in the human bladder. So suppose 3,000 bacteria are present at time t. That's giving you an idea of how this exponential function is being constructed. So here's your principal amount, and then here's the growth rate, and then we need to take the t minutes and break it into increments of 20. Not that you need to know about the structure, basically. You're not going to be asked to come up with these functions. You're just going to be given them and be able to work with them. So we want to see how many bacteria are present after t minutes, or 10 minutes, excuse me. So that means that t equals 10. And then here, after 1 hour, t is going to equal, well, how many minutes are in 1 hour? 60. Okay, so cool. So let's go ahead and plug this in. So n of 10 is going to be 3,000 times 2 to the 10 over 20 power. So we can reduce this fraction as we plug it into our calculator, which will give us 3,000 times 2 to the, what's 10 over 20? 1/2 power. You'd have enter the power into your calculator 0.5 if you want, okay? Which will be 3,000 times 2 to the 1/2 power, which is 4,242.640687 ... So this is just what my calculator gives me. And now, since we're talking about bacteria here, you should round to the nearest whole bacteria. So it's like a good final answer would be, after 10 minutes, we expect about 4,243 bacteria to be present. It's supposed to say to be present. All right, now how about after an hour? Well, t equaling 60, we'll plug that into our n function. We'll have 3,000 times 2 to the 60 over 20 power. What's 60 over 20 going to yield as I simplify that exponent? It'll be 3. So it'll be 3,000 times 2 to the 3rd power. That's going to be a very clean number because 2 to the 3rd power is 8, right? And 3,000 times 8, well, 3 times 8 is 24, and then you just kind of slap on 3 zeros after that. Nice and clean. Really didn't even need a calculator for that one. So then we'll say after an hour, or you could say 60 minutes if you like, we expect 24,000 bacteria to be present. Fun. So hopefully this helps everybody feel very comfortable dealing with exponential functions. And now we're going to switch gears over to logarithmic functions, which are the inverse function to the exponential. Okay, so logarithmics and exponentials are like the antithesis of one another. Okay, so in fact, the way that we define logarithmic functions, in order for it to make sense for us with the things that have already been established, is that we can rewrite them as exponential functions. So I want to make sure that I have some color-coded business with this. Let me draw, I'm going to use black first. So if we have y equals log base a of x, I have this mantra for it, which is to say that 1, the base is the base, which is to say that the base of the log, which in this case is this little a right here, is the same as the base of the exponential function version of it. So log base a is equivalent to a to some power, okay? And then the second part of my mantra in the conversion process is to say that the log is equal to the exponent. Log is equal to exponent. So in this logarithmic form, it's the fact that log base a of x is equal to y. If I was to convert it into its exponential form, the exponent on, the exponential expression would be the y. And then part 3 of the mantra, the exponential expression is equal to the argument of the log. The argument is the x in this case. It's going to be the thing that's inside of the log function, so to speak, okay? So I'll say exponential expression is equal to the argument. Okay, so if we have y equals log base a of x, that's the same as a to the y power equals x. And I want to make colors and shapes associations with this that are going to distinguish these. So let's do blue for the x, and we'll box it up. Okay. So the argument of the log is equal to the exponential expression. The next color will go red. So then the exponent on the exponential is going to be the thing that the log is equal to, right? That's the second part of the mantra. And then the base is the base. We'll do that in green. Do this brighter green, sure. The base is the base, okay? I will repeat this mantra every single time that we do this conversion process, starting with some graphing, okay? So here we go. We are slated with graphing y equals log base 2 of x. So this is equivalent to the following. The base is the base. So the base of 2 on the log is the base of 2 in the exponential function version. The log is equal to the exponent. The log 2 of x equal to y means that the y goes in the exponent position there. And then the exponential expression is equal to the argument, which is the x. Okay, so then you want to make an xy table, commonly associated with the f of x table as we were thinking about it before, but now we're just switching gears to think about these things in terms of y. And then what do we need to do? Well, notice that the y is kind of acting as the independent variable, okay? So I'm going to choose to put my standard 5 inputs in the y position, and that'll allow me to come up with the x outputs, but it's still going to be ordered pairs x, y in that order in order to like plot the points here, okay? So that'll be, the next value in my standard 5 is 0, which is neither positive nor negative, 0, 1, and 2. So if these are my inputs, I know it's a little bit weird to have y act as the inputs, but it's acting as the independent variable here in the structure of the equivalent form of the logarithmic function, okay? So plug in a -2 for y, and what do you get? Well, 2 to the -2 power, if you recall from the exponential, similar function, which would be the inverse of what we're about to plot here, was -1/4. You can go back to those calculations if you don't recall that. Sorry, -1/4 is what I mean to draw. 2 to the -1 power gives me -1/2, not negative. Oh my gosh, I'm so sorry. Please disregard the negative sign here. Yikes, it's just 1/4 and it's positive. There we go. Anything to the 0 power is just going to yield a 1. 2 to the first power is a 2. 2 to the second power is a 4. Okay, so let's go ahead and plot these ordered pairs. So x equals 1/4, and I'm going to do this with a bit of color to make it more fun. Let's go pink with it. So x being 1/4 is not halfway between these tick marks, but half of halfway. And then we go down to 2. So that's going to be very close to the y-axis. Okay. And then going x to the 1/2, it's halfway between these tick marks, but down by 1. We'll be right there with it. And then 1, 0 is right here. 2, 1 is right there. And then 4, 2 is here. So you might notice that it has this kind of same exponential growth look, but it's on its side. And that's only right because we're going to think about this logarithmic stuff as just being the x's and the y's switched from its exponential counterpart. Because again, that's how function inverses work. Not that we're going to spend pretty much any time talking about function inverses. It's something that you would talk about in much more detail if you were on a different mathematical journey here, getting into pre-calculus and levels of calculus, okay? But that's not something that's in your future, and that's okay. You're on a different pathway here. Okay, so let's go ahead and draw the trajectory. Basically, we're going to hug the y-axis. Oops, not cross it. Let me draw that one more time. I'm getting a little bit sloppy. You want to hug that y-axis. Oh, Lord, I keep crossing it. Ah! Let's try that again. Thank you for your patience, guys. Hug it, but don't cross. Yikes. Okay, I crossed a little bit where we're going to just ignore that and say that we grow in approximately this fashion, okay? Great. Cool. So that's what y equals log base 2 of x is going to look like. Now remember, you don't ever really actually use this structure in order to plot the points. You're going to write it in its exponential form using the conversion process with the 3-part mantra here. And then those ordered pairs are going to get plotted in the xy plane, and you connect them, and it's going to look like some exponential growth or decay model, but on its side, okay? And so we have a similar kind of a thing going on when the base is 2, if the base is greater than 1, you're going to have basically this kind of a look to it. And if the base is a fraction, like we're going to see in this third example, you're going to have a little bit of a different look to it. Okay, but let's do a base that's still greater than 1, and we'll have, again, this similar kind of a shape, but it'll be slightly different because the base is a 3 rather than a 2. Okay, so again, convert. The base is the base. The log is equal to the exponent, and the exponential expression is equal to the argument of the log. Boom. XY table, bust it out. But put your standard 5 inputs into the y rather than the x. If you keep that in mind, you can't go wrong with graphing this logarithmic function. Okay, so -2 in there. So what's 3 to the -2 power? Well, that's the same as 1 over 3 squared. 1 over 3 squared is 1/9. There you go. -1, 3 to the -1 power is 1 over 3 to the first power, or 1/3. Boom. To the 0 power, that's a 1. 3 to the first power is 3. 3 to the second power is 9. So hopefully that wasn't too fast. If you want to do some side work to actually perform these calculations, by all means do so. I'm going to pick a fun color. Let's do this light blue for the points. 1/9 at -2. So 1/9 is super duper close to the y-axis, but down by 2. Pretty much on it, but not quite. 1/3 is pulling a little bit away from that, but at the -1. We're going to cross at 1 again, and then 1 is going to be, so we'll go 3 and then up by 1, like so. Oh, that's 4, rather, sorry. Let me erase that. Oops, I meant right here. Right there, 1, 2, 3, and then up by 1. And then we'll go out to 9 and go up by 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then up by 2. Cool. Cool. And let's draw, to the best of our ability, a trajectory that goes through, hugs the y-axis. Oops, crap. Hold on. I'm having a hard time drawing just a line that hugs the axis but doesn't cross it. Okay, and then we go through all these points and loop up. Boop. All right. Cool. So again, that same kind of structure, but it really a steeper turn on the growth here. Okay, now what does it look like when the base is a fraction? Cool. Let's go ahead and entertain this idea. So again, let's do the mantra. The base of the log is the base of the exponential. The log's equal to the exponent, and the argument of the log is what the exponential expression is equal to. So there we go. Let's do an XY table. Okay, so do your standard 5 inputs in for y, not x this time. A little switcheroo. What's 1/2 to the -2 power? Well, flipping it, we'll give it 2 to the second power, which will be 4. 1/2 to the -1 power, that'll be flipping the 1/2 outright, which will be a 2. To the 0 power will be a 1. To the first power will be 1/2. And to the second power will be 1/4. Okay, just in the interest of time, I'm going to go ahead and go through those quickly. And if you have the wherewithal to calculate those on the side, by all means do so. Okay, so x being 4, I'm going to go out to 4, but then down by 2, which is right here. Here's 4, -2. Here is 2, -1. 1, 0. So we're crossing the x-axis here. 1/2 will go up by 1. So like that, and then 1/4 will go up by 2, which will be about right there. So you can see the path of this trajectory here. It's kind of like a flip over the x-axis compared to y equals log base 2 of x, and that's no accident. It's supposed to be like that. So now here the trajectory suggests that we're going to ride the y-axis, but coming from above. Go through all those points and just kind of follow the path as we have come to see it with other examples. Okay, so there's a very super rough drawing. So fun. Okay, great. General shape, as long as you follow that, you'll be totally fine. Let's go ahead and practice converting and also finding the exact values of some logarithms by reiterating this definition in terms of logarithmic functions and their corresponding exponential expressions or exponential equation counterparts. So if you have log base A of B equals C, okay, then that's equivalent to A to the C power equals B, okay? And then we can also, what were the colors that we used? Blue. Let me try and be consistent to what we did earlier. Okay, so the x's, we had an A, X, and Y with the original, but I'll let the argument be boxed up blue. Blue box for the argument. Blue box for the argument. And then it was, sorry, let me check one more time. Red triangle for the exponent. Red triangle for the exponent. Oops, red. And then it was green circle, I remember that one at least, for the base. The base is the base, the log is equal to the exponent, and the argument is equal to the exponential expression. Now, let's get that going with some conversions here. We'll do these exercises in this cute purple color, why not? So we're just slated with rewrite the each logarithmic equation into its exponential equation. We're not to then solve it by any means, we're just rewriting it. Okay, that's the only exercise associated with numbers 1, 2, and 3 with this example set. So remember the mantra, the base is the base, the log is equal to the exponent, and the argument is equal to the exponential expression. And that's it, just convert. or rewrite rather, is the word that they use. So that one's done. Okay, for number 2, the base is the base. So the base being 4, that's the base of the exponential. The log is equal to the exponent. And the exponential expression, 4 to the y power here, is equal to the argument of the log, which is the 7. Cool. One more time for number 3, the base is the base. The base of the log is a, so the base of the exponential is also a. The log is equal to the exponent, which is a -1. And that is equal to the argument of the log. And that is that. I'll box those up for you. We move on. Okay, now let's go the other direction. Let's rewrite each of these exponential equations as a logarithmic. I'll do those in this magenta E color. Okay, so the base is the base, so that means that this should be log base 2, because the base of the exponential is 2. The exponential expression is always equal to the argument, so that's what goes inside of the log, and the log is equal to the exponent, which in this case is x. Great. Let's say the mantra again, but for number 2 in this example set. The base is the base, so that means this will be log base z. The exponential is equal to the argument, so inside of the logarithm we'll put a 9, and that is equal to the exponent of -2. Great. One more time for number 3. The base is the base, so we'll have log base t of exponential is equal to 5, that's the argument, and then the log is always equal to the exponent of -3. And that is that. Done. Okay, next we're going to find the value of each of these logarithmic expressions, which I'm going to show you my trick to this. Okay, my trick is the following. Set each of these equal to x and then convert to an exponential expression and then solve. Okay, so setting them each equal to x, convert is the next instruction. So that'll be 5, so the base is the base, right? And it's base 5, and the log is equal to the exponent, and the exponential expression is equal to the argument. 5 to the x power equals 5. Well, anything that doesn't have an exponent has an invisible 1 exponent on it, right? And now we have exponential expressions on both sides of the equation that are the same base, so you can drop the bases, and therefore x equals what? X equals 1. So that is the exact value of this logarithmic expression. Cool. Let's do the same thing for number 2. The base is the base, that's 1/3, right, is equal to, or sorry, to the x power, because the logarithm is always equal to the exponent, and that's going to equal 9. Okay, we need to rewrite these as base 3. So I'll put off to the side that I want to rewrite them as base 3. Base 3. So this 1/3, the 3 being in the denominator space, I'm going to look at this and be like, that's 3 to the -1 power, but then it's still collectively raised to the x power. And then 9 can be rewritten as 3 squared. So therefore, this becomes 3 to the -x power equals 3 squared. Go ahead and drop the bases. Boom, boom. This implies that -x is equal to 2, which means that ultimately x equals -2 for this one. Okay, I'm going to start boxing up final answers now, because I am encroaching on the space for this last problem. And I'll do a little like that. There we go. Just to make sure it's clear what space I'm using for example 3 in this set. Okay, so the base is 4. So the base is 4 here in the converted stuff. So it'll be 4 to the x power equals 1/64. Yep, so this can be rewritten base 4. Oops, not the highlighter. I want to draw. Do base 4 for this one. You could also rewrite it base 2, but why, you know? Always pick the largest common base that's possible. So 64, if you're not familiar with that number as a base 4, it's 4 to the third power, but it's in a denominator space, so we're going to rewrite this as 4 to the negative third power. Now you can drop those bases. Boop, boop. X equals negative 3. Donezo. And we're going to box that up and call it good. Fun. Okay. Moving on to the last, I think this is the last page. Okay, yeah, so we have a couple of special examples in which we have some weird stuff going on. I'm going to continue to do the thing where I set it equal to x to allow for the ease of the conversion process, and that's going to help me find the values, okay? But remember your mantra, it's the same. The mantra is, we're going to go, since this is exponential, it's going to be rewritten as log base, what, 6? Because that's the base of the exponential. And the exponent is the thing that the log is equal to, so that'll be log base 6 of 2. I know, a little bit funky. And then the exponential is always equal to the argument. Now, notice that we have log base 6's of different arguments on both sides. Well, just so you can drop the bases if they're equal to each other and set the exponents equal, you can also do so with the logarithms as long as they're the same base. So it's just like dropping the bases with the exponential version of this, and you can set the arguments equal to each other, and that's how you're going to get x equals 2 for the value of this particular exponential expression. Okay? Fun. Let's do this again, but for this log, we're going to convert it into an exponential, and it's going to look like this. Oops, let me erase that mark there. That was unintentional. And so the base is the base. Oh, again, sorry, I'm touching the stylus to the screen when I don't mean to. So it's base 8, right? And the log is always equal to the exponent. And the exponential expression, 8 to the x power, is equal to the argument, which is 8 to the third power. We have exponential expressions equal to each other with the same base. Drop that base, boom, boom, x equals 3. Fun and cute, love it. Great. So let's remind ourselves of the conversion process in this last set here. And you're going to solve each logarithmic equation. So if you have a logarithmic equation, log base a of b equals c, that is the same as a to the c power equals b. And that's what we're always going to be doing, this conversion for each of these exercises to help us solve for x. Okay, here we go. For number 1, the base is the base. So this is equivalent to 3 to the second power equals x. Cute. What's 3 squared? No problem. That's 9. 9 equals x. Done deal. All right, number 2. 9 to the x power equals 9. What? What does x have to be in order to make this true? X equals 1. No biggie. You can think of this as dropping the base, having like a, secret 1 in this position right here, right? If you like. Or just say, well, what 9, what exponent has to be here in order to make this true? It's got to be a 1. Great. All right, for number 3, we have x to the first power equals 12. Okay, well, this exponent of 1 is really not saying anything at all. We could just straight up say we know that x has to equal 12 in order for this to be true. Cool. For number 4, x to the 1/2 power equals 9. 1/2 power, remember, that's the square root of x equals 9. What number, when square rooted, gives you a 9? X has to equal 81. You just got to give yourself the, the square of 9 to get that one going. Okay, and then lastly, I think this is the very last problem. It is. The most challenging by far, for sure. Nothing we can't handle, though. The base is root 2, and we're going to raise that to the x power by virtue of the structure here. The log is always equal to the exponent, and that's supposed to be equal to square root of 2 to the 9th power. Same bases. Use the equivalent exponent or equivalent exponential principle, I think it was called. What a loaded name. Drop those bases, x equals 9. Fun. Okay, so if you keep the three-part mantra in mind, hopefully you'll have a very fun time converting and solving these logarithmic equations. I know I do, but only after I figured out the trick, right? And that's going to be the thing that's you'll find this often true about mathematics in general, or in the mathematics that's involved in statistics, is that it's only fun when you get it. So if you're not getting some of this stuff, you want some more examples or want me to slow down and explain the conversion process a little bit more, let me know in class, okay? I'll see you then.